So this session is going to be 3 talks, each 15 minutes, and then we'll welcome back our speakers, like this morning, to the front and have a 20-minute Q&A. So save your questions until the end. And also, don't leave too quickly because we'll have a group photo at the end of this session. So stay in your seats at the end of the talks. So let's get going. We'll start with Peter Miersch from the Helmholtz Center for Environmental Research. Thank you.
Yes, thank you very much for giving me the opportunity to present here today. And thanks very, very much to the organizers of this very great conference so far. Today I'd like to present some work that my collaborators and I did on sensitivity analysis of causal discovery on simulated river flood data using nonlinear conditional independence testing. And because I know that this is quite a mouthful, this title, I will start off by explaining what it actually means and why it matters. So first, let's start off with river floods. So I come from the domain of extreme event research, and what I try to understand is how does this system work, where climate dynamics impact our meteorological drivers like snowpack, temperature, and precipitation, and how this then translates into a hazard, in my case, flooding, which then further translates into an impact, flood damage. And while I know that there are a lot more things modulating this, as we saw in the previous session, I will only focus on the gray area, which you probably cannot see very well here. So I just want to understand how meteorological drivers work for these floods and how the changes in these drivers translate into changes in the hazard discharge. And the goal of what I want to get is something like this causal graph there. It's an example where each of the nodes represents one of my meteorological driver variables, and the arrows, the edges, are causal links, where I have a causal driver that, for example, snowmelt drives discharge, here with Q, in this catchment. And we also have time-lagged effects, like, for example, precipitation is not only important for the same day, but also important for days before the event. And what I want to get is I want to get one causal graph for each catchment. And the question is, how do I learn this graph? Because we don't know it in advance. And before I go into this, I first want to describe the data that I'm actually using for this and why it's important that we have simulated river flood data rather than just observational. First, let's look at the observations. The observations are daily catchment averaged time series. So our features, precipitation, temperature, soil moisture, and snowpack, and the effect, river discharge. But the problem here is that we have a rather limited sample size in our observational time period, and we have possible confounders. And this motivates why I want to use a simulated discharge benchmark data set, where we use precipitation and temperature. We get just by resampling the observations in a way that preserves both the temporal structure and the seasonal cycle. And we get discharge, snowpack, and soil moisture using a state-of-the-art hydrological model, MHM. And the good thing is we don't have any unobserved confounders here. And this is then what the time series looks like, more or less. So on the top, we have discharge. This is our effect that we want to study. And on the bottom, in green, we have the 4 different drivers. And you can, for example, see very well that the temporal structure of temperature is still present, and that we also get snowmelt only in the winter month, where it's snowpack only in the winter months, where it's melting in spring. And then I want to study river floods. So I want to look at discharge peaks, only at the tails of these distributions. And while the definition that I use is not per se an extreme flood, I want to look at local distinct maxima that are then independent samples of high discharge events. And let's go on causal discovery. Why would I actually want to do it? The good thing with causal discovery is we can learn causality from observational data, and we can also very easily incorporate domain knowledge that we already have into our algorithm. And in this case, the algorithm that I use is the so-called PCMCI plus algorithm, which is a variant of the PC algorithm, a causal discovery algorithm, tailored to time series. And it's a constraint-based causal discovery algorithm, which means that it makes its decisions what the causal drivers are by conditional independence testing. And this then brings me to a very important point here, conditional independence testing. The idea of how it works is that we use regression and then a dependence measure on the residuals. And the standard that has been used in this domain mostly is partial correlation due to computational simplicity. But in this study, I know that discharge peaks have a nonlinear behavior. And this is why, this can be shown, for example, if you use linear regression to try to predict these discharge peaks, you get an R² on a test set of around 0.68, whereas with Gaussian process regression, a nonlinear method, you get 0.92. And this motivates why in this study further, I will just use Gaussian process regression distance correlation and nonlinear conditional independence test. BIOS update. I just skipped this. Oh, you don't see this. Perfect. So why do I actually want to do a sensitivity analysis? Here on the left, we have the same graph that I had on my first slide. And this is the same catchment where I do causal discovery using different subsets of my data set of independent samples. And I find that in one of these graphs, snow is important for discharge, and the other, it is not. So this data set should kind of bridge the gap between artificial and observational data and do this in a setting where we have no ground truth available. I don't know in advance if snow is important in this catchment. And the question I try to answer is, when do we converge towards a single causal graph? And just for the ones that are maybe a little bit more familiar with PCMCI, the parameters constraints that I'm using here is PCMCI+, the GPDC test, PyTorch accelerated. I use daily precipitation as a predictor up to 7 days before the event. I use average temperature of the 7 days before the event, and snowpack and soil moisture just 7 days before the event. First, I'd like to show some results that are for a single catchment. And the metric that I use here is the number of edges that you find in the graph. And not very surprisingly, you find more edges the more samples you have. And this can be easily explained. So on the x-axis, you have the sample size, and the y-axis, the number of edges that you discover. And the reason for this is that you always have some edges that are on the edge of statistical significance. And the next metric that I want to use, there's one slide missing, but it's in the, so the next metric I want to use is the fraction of links that are uncertain between graphs discovered using the same sample size. So if I have two graphs that I have discovered, I can just look at how many edges are different between those two. And what we can see here, as we do for this single catchment, not really converge towards a single causal graph. And if we now look at which edges are always found and which are only sometimes found, we first find that independent of the sample size on the x-axis here, that it's always found that discharge is autocorrelated. But we also find that a more complex relationship, like soil moisture, is only consistently found if we have more than, let's say, 1,000, 1,500 data points. For precipitation, we get this pattern that precipitation just very few days before the event can be found very easily, whereas precipitation rather far away from the event is not found very often. And we cannot find the rather more complex relationship between snow and temperature and runoff at all. And to summarize, so we fail somewhat to consistently discover the more complex relationship like soil moisture and snow. And to show you that this is just not the case for one single catchment, I will have the same graphs just for average over all the 45 catchments where we did this analysis. So we see the same trend here. The more samples we have, the more edges we find. The number of edges that are different between graphs of same sample size stay more or less constant. And we only get a very slight trend downwards where the fraction of the uncertain edges at the limit of computationally feasible amount of data is still rather high. And if we look at research, recent research that supports these findings, we can see that there are no studies on observed or simulated data using Earth system models. But we can find that in a technical report by Nicole et al. In 2023, they find that PCMCI is not suitable for the analysis of spatiotemporal data. And in another, in a submission to, in another paper from 2024, we find that the decrease of PCMCI performance for larger graphs under violation of the faithfulness assumption. And before I want to go to my conclusions, I want to go and show one positive note on this. So what you see here is the different, how many graphs are different between same sample size if you have in the observed time period. So in red, you see that for our simulated data set, we usually get somewhere around 3.5 edges that are different. But if we look how the graph from the observational time period looks in this context, we can find that we can actually see that the observational period has a different causal graph than our simulated data. So why does this happen? First of all, PCMCI has an assumption that we have faithfulness. That means that the condition independence implies deseparation. So we can show that PCMCI will converge under an oracle assumption where we have perfect conditional independence. However, PCMCI also has a very strong dependence on previous decisions. And this is where we have some violations. We have a finite sample size estimation error, which is also true if you use a nonlinear conditional independence test. And we require a sufficiently large sample size and even a strong faithfulness assumption. And additionally, statistical power of independence testing is dependent on the effect size and the dimensionality. And PCMCI, or the PC algorithm in general, has many different effect sizes and also many different dimensionalities of the independence testing. So it's impossible to perform uniform testing. To conclude, I would not recommend to just interpret causal discovery results without proper testing. And in general, you can use causal discovery as a very powerful hypothesis generation tool, but just using nonlinear conditional independence testing is not a solution to the problems that you might have with causal discovery. And there are algorithmic improvements that are necessary to reducing the path dependency of causal discovery. And with that, I'd like to thank you for your attention. If you have any questions, please ask at the end of the session in the panel discussion or get in contact with me via mail or anything else. Thank you.
Okay, next we have Robert Rouse from the University of Cambridge.
Great. Okay, so I'm here to talk about the use of Gaussian and neural processes in predicting streamflow. So you have to forgive me for the slightly non-specific title on the previous slide. I didn't think that one through. For anyone who's a hydrologist in the room, this might feel like the kids' roller coasters at Disney World. But for everyone who's not a hydrologist, hopefully this will give you a bit of a grounding and you'll be able to go on this fantastic journey with me. So why do we care about predicting streamflow in rivers? There's obviously a variety of reasons, such as future water resource management and flood risk analysis. And the reason why we might want to apply data-driven methods, so machine learning, to this problem is because there are a lot of hydrological models that are mechanistic or process-based, and there's a paper that came out a month or two ago in Nature Water that shows that most of them fall down around the world where they're not calibrated. Okay, whereas with data-driven models, we might be able to learn some of these patterns and generalize a bit better. So this is actually a subcomponent, what I'm talking about today, of a wider package, which I've been working on for a little while, which is on trying to develop those generalizing models. So again, keeping the kid gloves on, not just for me, for you, but also in terms of being able to build the best bad model possible. And forget the formatting, this was submitted as an image, but it's kind of broken. We're going to take streamflow and treat it as a simple input-output model. in terms of precipitation, evapotranspiration, plus change in internal storage within the catchment. I've worked with this on a lot of catchments, but I've just chosen 3 to show you today. They're very different, and the reason for obviously wanting to use lots of different catchments is because we can kind of test how well the model performs in different regimes. So we've got, within the UK, these are all UK-based, the River Severn at Hallbridge. So this is one of the largest catchments in the UK, through to a very small catchment, the Fine Horse at Chinati, which I think is the pronunciation. It's somewhere in Scotland. I'm probably mangling it. It's very small, it's very mountainous, so it's a lot flashier. Okay, so we can kind of see how the model holds up across, areas of different geology, different land use, and different topography. So in terms of the assumptions that I'm making here, one is that the catchment data, which is from CEH, is correct, and that it's not wrong. Same goes for the catchment boundaries, and that these catchment descriptors aren't changing over time. Now, for geology and topography, that's definitely the case. For land use, that's less so, but for reasons that I'll get onto at the end, it doesn't matter too much in this case. Secondly, the data from ERA 5, I'm also assuming is good enough to use without needing to do too much interpretation. And then finally, that a lumped catchment modelling approach, so that's basically taking the meteorological parameters that I'm using as inputs and averaging them or interpolating them, as is the case for very small catchments, is a suitable thing to do. So that change in internal storage obviously isn't a meteorological variable, and typically people will quantify this through measures such as soil moisture. And although this isn't a neural process or Gaussian process model, I did check that what I did use instead, which is a statistical parameterization of meteorology in place of the soil moisture, is a suitable swap to make. So we can see in the top left, and apologies in the back, you may not be able to see too clearly, but using 7 days worth of meteorological variables, so that's precipitation, temperature, wind speed, and humidity, gives us pretty good prediction. Moving towards 28 days gives us better prediction. If we then go back to 7 days and use soil moisture, we get a better prediction again. But if we just throw the soil moisture out the window and use these statistical parameterizations instead, we end up with an even better model that is just using meteorology as inputs. So hopefully a very simple model. And as to the Gaussian process and neural process models, I'm not going to go into them too much because the people who have written, either the paper, so Marta Gunello, who wrote the paper on neural processes, or Carl Rasmussen's book on Gaussian processes, can do a much better job than I could in 15 minutes, or possibly at all. But what I do want to highlight is the fact that with a Gaussian process, what we can do is we can encode our prior beliefs about how the system behaves. Okay, so through the kernel function. And this just toy data problem at the bottom is one which has periodicity. So we can say, in the kernel function that there is periodicity present, and what it ends up being able to do is obviously match that, and then it extrapolates well. So it doesn't just interpolate well, it performs extrapolation quite well. And that's quite key for hydrology, because as rainfall exceeds and continues to grow, we would hope that our predicted flow would also grow according to whatever pattern we might believe is there. As for the neural process, again, I'm not going to go into this too much, but essentially what you have is an encoder where you feed it some input and output pairs, and it learns a representation, and then you aggregate the representation, and then you use that aggregated representation to form parameterization, and then from that parameterization you draw samples and combine it with new inputs to perform to basically get target outputs. Okay. Again, I would recommend reading the paper because they're pretty nifty models, and it's through that parameterization at the end that we can basically get uncertainty for this model as well. Okay, so these are both probabilistic models. Now, in terms of the kernel design, at a very simple level, if I just look at the preceding day's worth of precipitation compared to streamflow, we can see that that there's sort of like a linear pattern here, right? So as precipitation goes up, as I mentioned earlier, flow also goes up. And we can kind of carry this on over a few days. So this is just a general linear model over 7 days. And we can see that although the predictions aren't great, and there are most likely non-linearities present and other variables that need to come into this, there is a very strong linear trend observable between each of the days' worth of rainfall and its impact on flow. So that kind of gives us like the starting point for our kernel design. And what we actually end up doing is, you see this a little bit with temperature as well, which is probably understandable. As the temperature keeps getting hotter, you would expect there to be less flow, because more of that rainfall that lands in the catchment is being evaporated, and what's present in the soil is also evaporating as well. So we basically end up combining linear and matern kernels to end up with a composite kernel from which we can then make our predictions. So for each of my 3 rivers, I'll go through the results for a sample year in turn, very quickly, mind you. And they're all pretty good, but they're good in slightly different ways. And what I've got here is the Gaussian process and then the neural process, and then I've also thrown in something called a sparse variational Gaussian process. And the reason for me wanting to compare this in addition to the other two is to do with computational complexity. Now, it turns out that this ends up, with modern computing being a relatively minor issue, given the size of the data set. But the computational complexity for GPs is about order n cubed. For neural processes, it's m plus n, where m is the number of context points and n is the number of target points. And then for the SVGP, it's nm squared, where m is the number of inducing points. Okay, so what you would hope to see is that the GP would probably take longest, the SVGP would take somewhere in the middle, and the NP would take less time. Okay, and whilst that is the case, the other thing that happens is that the neural process, as you give it more data, actually becomes really certain about its predictions. And that may be, in some contexts, a behavior that you want, but it's actually, in this context, a behavior that I would have liked to have avoided. Because we don't have too many flood events, right? As the previous speaker mentioned, they're extreme, they don't happen very often. What I would really like my model to do is to actually have that uncertainty blow up around the extremes. Okay, so it's going to spit out a prediction say, this is what I think is going to happen, but it could be anything within this range because this is quite rare, I haven't seen it before. And the GP models do that quite well, but the NP model actually doesn't. As I just gave it more data, the mean prediction obviously got a lot better, but as I said before, the uncertainty collapses. And it's the same case for the Bedford ooze at Roxton. But then when we get onto the Findhorn at Shinashi, as I said, this is quite a small mountainous catchment, so it's very flashy. And although the pattern between GP versus NP is the same, the predictions start to degrade slightly in this case. So the previous two models are very good, and this one is not so much. Okay, and that's basically because some of the assumptions that I made at the beginning in terms of how I was thinking about this temporally start to come apart for smaller catchments. And again, I'll get on to how that gets addressed towards the end. So this is just a giant table. I know people hate them in presentations, but as you can see, the NSE, which is like a standard metric in hydrology for assessing the performance of hydrological models, is pretty good for all 3 models for both the Severn and the Bedford ooze, but less good at the Findhorn. And then what I've also done is thrown in a metric from a paper which is in press at the moment called reflective error. And what this does is it gives you an idea as to how well your model is predicting extremes compared to what I term routine data, so stuff that's essentially close to the mean. And a score of 1 here means that it's all the errors at the extremes, and a score of 0 would mean it's all at the mean. And what you end up with is the GP models are actually slightly better at predicting extremes. And it's because of the fact that I can tell the model in the kernel function, when you have high rainfall, you're going to have high flow, and it responds accordingly. And as I said, time, the GP takes a lot longer to solve. But again, I've already said that, but perhaps it's not an issue with modern computing and when you have only about 10,000 data points in the training set. So In terms of how this goes forward and how it gets improved, thinking particularly about the Findhorn at Shinashi, well, I mentioned that this was part of a wider project, so building a generalizing hydrological model, and I'm not presenting the results of that here today, but if we can actually combine area with those meteorological variables and with other things that tell us whether or not a catchment is flashy or not, and learn from some of these flashy catchments, then we can start to predict better for them and get around that issue. Doesn't obviously help this problem setup and its assumptions. They're clearly not right for the Findhorn. But when it comes to making that generalizing step, a lot of those issues just start to fall away, and we end up with, even for the small flashy catchments in the generalizing hydrological context, we end up with an NSC of 0.75 to 0.8 on average, and for the very large catchments it actually approaches parity. Some of them are as high as 0.95. So that's a way to get around some of those issues. Is the kernel design the most optimal? I mean, this is a very high dimensional problem compared to that toy data problem I showed. Obviously with the periodic one, you can kind of see that very easily, but you can't see problems in 20 dimensions all too well. So it becomes a bit more challenging, and maybe our kernel isn't the best kernel design. Maybe we should choose a different one. But then the question becomes, if we don't know what the kernel is, then why are we using GPs at all, right? We could just use a Bayesian neural network and be done with it. And then, I guess, as I've already mentioned, the MPs and their uncertainty isn't ideal behaviour. I've spent a lot of time trying to tinker with them to try and coax them into maintaining high levels of uncertainty around extremes, but they're just not having it. They don't want to play ball. And then finally, I guess the question is, as with all problems, is our input data set complete? Okay, maybe we're missing something. And certainly when looking at some other catchments that I haven't mentioned today, so there's one in the UK that's basically bordering on an ecological disaster because someone thought it would be good to abstract 95% of all the water. This model basically doesn't work there at all, because how can you predict that if you don't know that that's an input, right? So that's a challenge, and that's something that we do also resolve when looking at the generalizing approach. So lots of pluses from these. The MP model I did take forward because the generalizing model has 1 million data points, so it works quite well. The standard GP, not so much. It takes far too long to solve. And I guess if you're interested, keep your eyes peeled for when we do actually eventually publish the full generalizing model. Thank you.
Thank you, Rob. And last but not least, James Briant from University College London.
Okay, so thank you very much for the organisers for letting us present here, and also, I'm James Briant. So I'm a PhD student at University College London in the Department of Statistical Science, and I'm going to present some work that I've been working on for almost a year and a half now. So Dan Giles is also working on this project in the audience near the front, and we've been working with my supervisor Serge and our colleague Cyril at the Met Office. And we're going to be presenting a hybrid machine learning climate simulation using high-resolution convection modelling, which I appreciate is also a mouthful. So climate models operate on too coarse a resolution to properly resolve the cloud-generating processes. And this has been a historical problem in climate models for a long time. Our big idea is, can we somehow capture the variability that is present in the outside world but also in weather forecasts, and somehow inject that variability into the climate models? So our approach to do this is going to be to consider the temperature and humidity profiles if you consider one particular column of cells in a GCM. So what we've plotted here, well, we haven't plotted this, but what we've got here is just a temperature profile going through the atmosphere. What we're going to do is use the current temperature profile and a few other variables that I'll come to in a minute to try and predict how much this red line, as it goes through in altitude, varies. And what these black arrows represent is how much that red line might swing in one particular location. And you can think of that as the variability of the temperature in that particular location. I should point out that the black arrows here are not necessarily representative of the uncertainty or the variability that is present here. They're just to get the gist of what we're going to do. So what inputs are we going to use? So we're going to start off on the left-hand side. We're going to start off with the air pressure at the lowest level of the atmosphere. And then we're going to look at the temperature field for each layer of the atmosphere as we go up. So in this case, I've just highlighted it as N, but it'll turn up that's going to be 8 values. We then do the same thing for the specific humidity inputs. And then the final 3 on the right-hand side, we're looking at the orography. So if you imagine for the climate model, those grid cells cover quite a large area, and the orography can vary quite significantly in that area, in that particular grid cell. So what we're considering here is the mean of that non-random function of land and how much it varies within that particular grid cell. So that's those 2 there. And then we have the land-sea mask as our final input. We then train a statistical model to learn the relationship between those inputs and the variability at that particular column of cells. So we predict the variability in the temperature field for that particular column. So we've got 8 outputs there in this case, and we've also do the same thing for the specific humidity. So there is similar work. So this was also done by Brenovitz and Bretherton a few years ago. However, they use a neural network to learn this relationship, and they also only perform this on an aquaplanet model. Whereas what we're going to use is a full, a very simplified climate model. And therefore, including these orography mean and the land-sea mask variables at the end is, of course, novel. Okay, so what am I going to present? So I'm going to show the high-resolution training data that we use to learn this relationship. I'm then going to show you how we do this, learn this relationship that predicts the variability in the temperature and the humidity columns. And then we're going to embed this statistical model into a coarse resolution climate model. So let's start with the first. We need some data. So the data comes from a very high resolution model. It's a limited area model that uses 80 uniformly spaced models by the Met Office. This comes from the unified model. You can see those points at the bottom right here. I'm afraid that's not a huge picture, but it suffices to say that they're roughly equally spaced. We've got plenty over land and plenty over sea. Each one of those boxes is 512 by 512 grid points. So there's a lot of data in here. And actually, this model is run for 1 month. So we have 1 month's data that we could use. So we take each one of those boxes, those high resolution limited area models. We chop out a border around each edge, and we call that spin up. And we divide what's left by 4. We do that because each one of these colored small subregions is approximately the same size as the cells in the climate model. So we can expect that the amount of variability present in the training data should be roughly what we'd expect. And splitting the data up in this way means that we actually have about 38,500 training points. We don't use anywhere near that many. We use only 500. And we actually only take those 500 from the first day. So actually, all of the training data that we use is from the 1st of January. I should say that some of the, this has actually changed a little bit in the last couple of weeks. And I haven't had a chance to update this. I didn't realize it hadn't changed, but it's not changed by much. So the model that we're going to use to learn this relationship is a Gaussian process model. 15 minutes is not long enough to introduce Gaussian process models. Suffice to say that we're able to predict the mean relatively well, and the Gaussian process models also provide uncertainty estimates, which we use later on. What I will say, however, is that we use the MOGP emulator by the Alan Turing Institute, and we use this because it has some really nice parallelized optimization procedures that allow us to effectively fit lots of Gaussian processes all at the same time relatively efficiently. Okay, suppose we've trained our Gaussian process model to learn that relationship. I'll give you some kind of visualization to imagine what's actually happening here. So imagine we've taken a snapshot of the atmosphere, and we have put in or input the temperature and the humidity fields into our Gaussian process, and we tried to predict how much variability would you expect given those inputs at each location. And that's what we've got here. So on the left-hand side, we're looking at a snapshot for the 1st of January. On the right-hand side, we're looking at a snapshot for the 1st of June. And on the top, we've got temperature, and on the bottom, specific humidity. And we're quite pleased with these plots. They quite clearly show seasonality differences and differences in picking out the ocean and the land and the an update. Please don't do that. Okay. Yeah, so it's picking out mountainous regions and flat regions really well. So we're very pleased with how this is coming. Okay. And we've got validation plots. So we've got a few different variations of the validation plots. This is one particular example. So imagine one grid cell at one particular time point. We've taken the state of the atmosphere at that location through the Gaussian process and made a prediction on the outputs. And what we can see is that the temperature and the humidity fields are represented relatively well in terms of their mean prediction. But we're also aware that our uncertainty estimates are not brilliant, despite the fact we're using Gaussian processes. And we are very much aware on this and have been working on it for quite some time, trying to improve this. We are getting there, I think, but there's still clearly a lot more work to do. But suffice to say that we're aware that this is a problem, and we try to work around it as well. So, if we train the model, we now need to implement it into the climate model. The climate model we're going to use is called SPEEDY. SPEEDY is a Fortran model. It's very coarse resolution, will run on your laptop, and we couple it, how we couple it, I'll explain in the following slide, but we couple it using our own in-house Python wrappers. And we develop two different data sets. So we have our SPEEDY data set, which we just let SPEEDY run, and we also have our hybrid data set where we try to augment the dynamics of the model as we go. Like I say, we have two different data sets. Both are 10-year simulations. And what we do is every 6-hour forecast, we stop, output the state of the atmosphere, and then for the hybrid run, we run it through our Gaussian process, we make a prediction on the amount of variability, we take that variability estimate, and we generate a bit of random noise. So you can see that term at the very bottom, and for each cell, we take this random noise and add it on. So you can think of it as picking up the whole atmosphere and giving it a big shake, and then letting it run again for another 6 hours, and we see what happens. Let's skip over. Oh, yes, so this is indicating that actually what we also do in this case is we take our uncertainty estimates from the Gaussian process and add this onto the outputs from our Gaussian process as well. So we're basically saying this is how much variability we expect, and then we're adding on this much to just give it a bit bigger shake. This slide emphasizes what I've just said, but I'm actually going to skip over it in the interest of time. So, does this break anything? No, which might be a surprise. It certainly was to me the first time I saw it run. What we're looking at in this particular slide is over the whole 10-year forecast that we're predicting. In the top, we're looking at the annual difference between the SPEEDY and ERA 5, so that's just where we've let the climate model run. On the bottom, we're looking at the difference between the hybrid model and ERA 5. And most notably, you can see differences roughly in the sea between, I guess, between India and Madagascar. There's quite a significant reduction there. And also just off the southwest coast of Mexico as well. I've put on here 24% reduction area-weighted RMSE. I believe this has actually changed, and we're now looking at near a 40% RMSE reduction in some metrics. Mostly this is due to the way that the interpolation was done for the ERA 5 data. So we're certainly looking at some relatively big improvements for our precipitation estimates here. And we've tried to come up with ways that we explain how this is the mechanism through which this is happening as well. So if you imagine for one particular location, we're able to calculate some lifted index values. And lifted index is basically a measure of atmospheric stability at one particular time point. So for our 10-year forecast, we can calculate lifted index values for that location throughout the whole 10 years. And what we're really looking for is values below -4. Below -4, we're getting much larger precipitation, bigger storms. And we're seeing this come across in some locations. In this particular case, this is somewhere in Central Africa. And what you can see on the plot on the right-hand side is that not only have we got more counts of precipitation, we're also getting more extreme values from the right-hand side. And we believe this is the mechanism in some places. In others, we've also been looking at the Hadley cell. And again, I'm not the right person to explain the Hadley cell to people, but for those who do understand it, what we're looking at here is the difference between the Hadley cell just to the west of Mexico, where we saw that particularly big change earlier. And this is looking at the difference between the Hadley cell in the hybrid and the speedy run. And you can see that the reduction in the temperature gradient it starts to explain some of the less precipitation we're getting around the mid-latitude areas. Okay, so to conclude, we've managed to coarse grain some high-resolution data from some GCM runs. We've trained a Gaussian process model that's able to then predict the amount of variability you'd expect in the atmosphere given the current state. And we've coupled this Gaussian process to a very simplified GCM model that augments the dynamics at runtime. We've showcased that this can improve some biases in the model, particularly with precipitation, but also we've also been looking at cloud formation as well. And I'd just like to finish off by, we were really interested in your feedback. So this is the audience that we've really been trying to target with this research. And I'm aware we've got the 20-minute conversation coming up, but also please do send us an email. So if you scan that QR code, it will send me an email, which is that one. But yes, we'd love to hear your thoughts, and please come and speak to me. I'll be here all evening as well. So please, thank you.
So now I'd like to invite all the speakers back up to the front. Have a seat. And while I get the virtual questions up, shall we start with a question from the room? Yeah.
I can ask one. On the last talk, yeah, thanks for the Gaussian process bit over here. When you said you tried to improve the Gaussian process, massively underestimating the uncertainties for the humidity, what did you try? I mean, I actually had this problem with one of my emulators, but it'd be interesting to hear what you did.
Yes, so we've tried transforming some variables. We've tried changing the scale. We think scale is perhaps the biggest problem. I'm also aware that there might be... I'm concerned that the relationship between the inputs and the outputs is perhaps not as strong as we might be expecting. And I'm also aware that the choice of kernel is perhaps an issue as well. So I know, as it was mentioned earlier by Robert, I think the choice of kernel is perhaps having an impact. So there's, in a way, there's almost too much to consider to keep trying. And I think it's just going to be a long process of just ruling more things out.
Right, thanks.
Which is a non-answer, to be honest. Sorry.
Mine was because I wasn't including enough of the variance in my principal components, but you're not doing a dimensional reduction like that, are you?
Not currently, but I have tried doing that to see if it makes any difference. So far, very little.
Yeah, thank you for your talks. James, I have a question. What is the cell size in your model and how to choose this size?
Do you mean for the climate model?
yeah, you mentioned like cells. What kind of cells you're using? Yeah, could you just
So I think
explain and what is the size and how to choose?
so that cell size is determined by the climate model that we're using. I think it has a 96 by 48 grid size, and that's globally. So they're large, very coarse. But as I say, it runs on laptops. So I don't know exactly what length scale that is. I don't know if 30. 330 kilometers. Thank you.
Maybe we can take a question from online. So there's a question to all of you. It looks like you all use ERA 5 in your work one way or another. How do you see the strengths and limitations of the data in your own work?
Who wants to start? I don't use ERA. Well, apparently only 2 of us use ERA 5, so. Yeah, I mean, obviously the reason for using ERA 5, just on like on a surface level, is quite a straightforward one. It's globally available. It's relatively easy to get a hold of. Is it perfect? No, it's not. In terms of why, for my work, whether or not that's a huge issue is, I don't believe necessarily that it is, because the idea with this global generalizing hydrological model is eventually to force it with GCM data or interpreted GCM data using some bias correction and downscaling approach. So there are going to be issues along the way, and I think at some point you just have to make a decision and cut off and say, well, some error I'm happy with because just going further would make the model unwieldy, or there would be other issues with using that data. It might not be globally available, etc. So it's just a case of where picking and choosing your battles and where you want the balance to lie. Is that a cop out? It might be.
James?
Sorry, what was the question?
What are the limitations of using ERA 5 in your work?
So I suppose in our work, we're not using it to learn anything. We're more using it as like a benchmark to see how well is our approach performing. So I don't know that the question quite applies in the way it was maybe expected.
Well, if the person who wrote the message could follow up, that would be great. But in the meantime, let's take a question from the audience here.
Question for Robert. You've been using 3 catchments, if I'm not mistaken, for the Gaussian model. Were they all based in the UK? Because then why would you use the ERA 5 and perhaps not use something like a hydrological data explorer? Where
Yeah.
it's longer term data. Also, were you using them just for a month? Were you analysing, or was it longer term?
Yeah, sorry. I probably was perhaps a little unclear. It's I didn't just work with 3 catchments. I actually worked with about 150. The reason for using the ERA 5 is the initial build up in this approach has been using UK CEH data. The plan is now to pivot quite hard towards areas where there's no data at all. So one of the big challenges is going to be the Nile, which is a significantly bigger river in terms of length than what we have in the UK. So the catchment description approach is going to change slightly, and obviously we need to have a lot of flexibility in terms of the data that we're feeding into it. And one of the colleagues I'm working with at Cambridge, who he's the one who's specifically working on the Nile, doesn't have a lot of data for a lot of parts of the Nile. So what you can use in terms of weather is ERA 5. That's pretty much it. Now we could obviously perform some correction to ERA 5 data using, I know he's in the audience, like Deep Sensor Net, which Tom Anderson, if he waves, worked on, and that'd be a pretty good approach. But again, like I said, we just kind of have to have this global ubiquity element at play, and also the ethos of, I wasn't kidding when I said the best bad model, right? Because you're going to have data issues when you're looking at areas in Africa, South America, etc.
Of course. And then just one final thing, it's Shinaki.
Is it?
Yeah.
Okay, great. Now I know.
Thank you. I have a question for Robert. If I understood correctly from the slides, wouldn't the Gaussianity assumption of GPs be violated in your data? Since you're predicting flow rate, which should be positive, I guess. You're also mentioning the cases of extreme events, which I can understand the appeal of having a Gaussian process with higher variances in those cases, but I guess if we look into the samples, right, like samples from a Gaussian wouldn't actually match like peaks and then regular data. Could you talk a little bit more about that?
Yeah, sorry. I think your question's in two parts. I guess I'll answer the first one. So are you asking why, is it just why I'm using a Gaussian process at all?
No, it's more like, shouldn't you need to warp your Gaussian processes?
Oh, yeah. So I did actually look at warped Gaussian processes as well. And there's also, the question of, is it a Gaussian likelihood too? The warped Gaussian process didn't actually offer any improvement. So I kind of just considered it as an unnecessary embellishment. Whether or not I use a non-Gaussian likelihood, that's a valid question. I probably should be, especially because the actual distribution is really a log normal or a gamma distribution. And yeah, that is something that should have been on the further work slide, but wasn't.
Yeah, thank you.
So my question for James. So you find that there is a quite a big difference between the Aero 5 and your both the hybrid and both the speedy. Do you think that this is the case because the climate model you're using is so simplistic? And if so, when you go to let's say the real big climate models, do you think too that the improvement will be that big as you find in this case, or not?
So yes, I think it is a big difference because we're using a very simplified climate model. And I think you're probably right. I think we would expect to see smaller gains if we went to a proper climate model, I suppose. That is very much the next steps. But of course, the engineering problem of setting all that up is quite significant, which is why we've kind of stuck to a very simple model so far. The plan is eventually to do that. The timeline of sure, but yes and yes.
If I can briefly to Peter, when you say you are speaking about causality, what do you mean? Is it like statistical causality? Can you express more, tell us more? You're speaking about causal discovery.
Yes.
And you want to find a causal network graph. What is the cause and effect here? Is it a simple past, like a correlation between the past value of one variable to the next day, or there is some mechanical cause effect here?
So in a sense, it is a statistical definition of causality. It goes along the lines that often when you use statistical inferencing, you look at association between variables, but you don't only want to, sometimes variables are associated or correlated with one another even though there is no causality. So there are algorithms that tap into these ideas that have been developed by Judea Pearl, mostly on how you can define causality and how you can use it in statistics. And these causal discovery algorithms are meant to kind of distinguish between non-causal associations and actual causal relationships between variables. So in this sense, yes, it is a statistical definition of causality, but it should go beyond just predicting a variable.
Yeah, let's take one more question and then move on to one from online.
All right. Hi, I'm Viviana Quaviva. I'm from the City University of New York and Columbia. I have a question for Peter. I really enjoyed your talk. I work with these methods a little bit, and I was really relieved to hear you end saying a really proper testing is needed. So I was wondering if you can tell us a bit more in your experience. Do you think it's sort of testing before you start, check if your variables satisfy the hypothesis of different methods, or maybe like, testing after you obtain your graph, coming up with sort of consistency checks that you think, or both? Do you have, a favorite approach to testing?
I think you should, thank you for the question first. I think you should do both. First, you should check whether the assumptions that you have, so that you have no confounders, if you use an algorithm that requires that, is actually given, whether the independence test that you're using, if you use a dependence test that requires linear relationship, whether this is actually true. So you can look at the distributions of your data and look whether they actually match what you require in your test. But what I found is that even if you make sure that this is the case, then you will still find that the algorithm will not converge towards the same result all the time. So even though you might satisfy or think you satisfy all of your conditions, at least more or less, you still find that you do not get a consistent result. So you always have to do some after the fact testing. And I think the reason why this is not done usually is because in a synthetic data set, you can just look whether you have a ground truth, you can calculate the false positive rate and the recall and everything. But if you have real world data where you don't know the actual answer, you cannot really calculate these things. And this is then why I went into generating this big data set, which hopefully models the processes that are in my real data quite well, where I can then do these tests, at least find a consistent graph without saying that it should be correct, but at least gaining some more confidence in the correctness of the graph. However, if you have other applications of this, for example, there was a slide missing in my presentation for some reason. So if you have either a relatively simple network or you want to use it as a feature selection tool, then you don't have to worry about this as much. Right? So if you want to use it for feature prediction of a neural network, then you don't have to worry whether you might find some wrong features some of the times.
Thank you. Okay, so from online, this one is to Robert. One common limitation for GPs is their lack of scalability. How have you seen it addressed in hydrology?
I mean, beyond the obvious, which obviously mentioned, which is using sparse stochastic variational GPs, I haven't seen a huge amount of literature that's tried different approaches to dealing with scalability. In terms of my experience, with these single catchment models, because I'm using about 30 years worth of data to train, and then 10 years worth of data to test, and 1 or 2 for validation. The scalability isn't really too much of an issue if you don't mind waiting like an hour for the model to run. When it came to obviously using the generalizing model, set A with catchments and then predicting for set B, I used the SSVGP. The issue there wasn't actually the computational intractability, because they still solved pretty quickly, with appropriate M, so the number of inducing points. The issue there actually became the kernel design, because when you're dealing with things like, I know that there's abstraction. How does abstraction change things? In conjunction with the catchment descriptors, actually specifying that prior became quite difficult, and compared to something like the MP, where you can just get away with throwing in like a very standard ANN as the decoder and encoder, the predictions just weren't quite as good. So I'd actually say that when you've got like really big problems, it's often not the data. The problems that I work with is not the data that's the issue.
Yeah, so maybe we could open it up to our other 2 speakers. So you all use Gaussian processes. How did you go about choosing your kernel design, your priors? How'd you set it up?
So we've tried to keep ours as simple as possible, for better or for worse, to be fair. And I think this is something that we do have to revisit for our project, given how you saw how the GPs are struggling. But we've kept everything as Matern 5/2, and priors we've kept relatively basic as well. So I'm afraid I haven't got much to add other than we've kind of left it relatively simple, as I say, for better or for worse. Probably for worse.
Yeah, I can kind of say the same. We left it relatively simple, and the reason there being that we use it as an independence test, and that means that we use Gaussian process regression for various variables to predict various other variables in different dimensionalities. And this means that we cannot really use a very informative prior or use a very specific kernel, because the things that we regress are so different in the algorithm.
I think what I would like to add to ours actually is that what we've done so far has mostly been a bit like a proof of concept, I suppose. So although we've been kept it simple to start with, but now we've shown that the idea is working, we can now go back and revisit and see, okay, we actually need to do this properly to get the better fit, to eke as much performance out of it as we can.
Yeah, are there any final questions from the audience? I'll just get the last few online. So to Peter, PCMCI plus is a causal method that works on a time series without spatial encoding. Encoding the spatial variability of catchments would be a good or possible idea?
So in the group of Jakob Runge, who's developing a PCMCI, they are currently working on like regime PCMCI, where you use some kind of hot encoding for spatial variability. However, this would add another layer of complexity, and this is why I have not considered this. I would, for the work that I do, rather be interested in like seeing the differences in causal graphs between different regions, so different areas, rather than encoding it. However, if this would be possible and actually work, I think it would be very, very helpful and very good, cool thing to do.
And then the last question is to James. On the lifted index for lat-lon, have you considered creating maps for these with the flagged regions, so lower than -4, to see the spatial distribution? So I think it was referring to, yeah, the lifted indices and...
No, we haven't.
Yeah.
But we probably should.
So yeah, my question. Thanks both of you for the talk. But on the comment that you made about the neural process maybe underestimating uncertainty, and also related to what the other question, but I guess the probability that you're predicting is conditional on your inputs, and of course then I was just curious on your thoughts and also on the experiment that you were reporting it. So was it a single catchment model? And if so, would it be possible that the uncertainty is just shrinking because that conditional probability is very well mapped by the neural process and it doesn't need to blow up for extreme events because it basically learns the catchment dynamics? Or was it for a kind of multi-catchment or kind of predicting in engaged areas kind of problem, and what are your thoughts on that?
Yeah, so it's the model was tested for each catchment individually in terms of what I presented. Sorry. As for the uncertainty, yeah, you're right. I think what's going on is it is fairly well captured by the data that is being presented to the model, but the model is still, like that mean prediction is still not great when it comes to extremes. And it would be nice, I guess, because obviously, you know, with the GP in the kernel design, obviously if I make the kernel non-stationary, as I start to move away from the data, it diverges because it becomes less certain. To have, you know, seen just a few examples of an extreme event and then be overly certain is probably behavior that I would rather avoid. And it, you know, this is just my experience with neural processes, is that the uncertainty with these problems kind of collapsed everywhere simultaneously, rather than, you know, dropping where there was the most data and remaining high where there was very little. Does that answer your question?
Yeah, it does.
Okay, so with that, let's thank our speakers again.